Yeah, you hear me?
Yes.
So good morning. So let me remind you, first of all, I would like to mention that, some people ask me about chapter 2. So all the chapters of this book are available on so the book has monograph. So nonlinear discrete optimization has 6 chapters. Chapters 1 to 6. And the book is really ready. It's going to be out in 2 weeks. It's in print really, so 2 weeks is going to be out. And I'm going to put a link in my webpage, but for the time being, there are these preliminary lecture notes or preliminary earlier version on my website. So this is linked either from the website of this workshop. There's a link there, there's a description, and or you simply can go to my homepage and then it's linked there, lectures. And there are, chapter 2 is there too, so you have the 1 to 6. Chapter 6 actually is just linked to papers at this point. But all the chapters are there. I simply skip chapter 2 in the lectures here, and I'll come to that at the last lecture on Friday, hopefully. So I simply changed the order a little bit. So we talked about chapter 1 so far, the introduction, chapter 3, and now we're going to talk about chapter 4. So let me just remind you the main outcome of chapter 3. So last 2 lectures. Chapter 3. The main outcome was that we can do in polynomial time. So there was this couple of theorems actually, so not one, there were theorems. Given the Gradual basis, of A, then we can solve in polynomial time various linear and nonlinear integer programming problems in this standard form. Min or max, mostly min, but so this was what we developed in the last 2 hours. Define the Gradual basis exactly, slowly, two lectures ago, and then we last time we saw that we can solve this problem, minimize a separable convex function, in particular linear function, all sorts of LP norms. And I mentioned something about maximization. So actually maximization, we need some more material from chapter 2, and this will become later, so it's not directly just from this. Okay, so the problem is now that we need a Gradual basis. And the Gradual basis is a hard object. You played a little bit with this, so you try to compute some examples. Actually, before going to chapter 4, let me mention one thing on the Gradual basis. So after I introduce it, you try to compute some Gradual basis of small matrices, and then there was immediately this question: how do I know that I have enough vectors? Because it's unclear. I mean, the decision problem, deciding if a vector is in the Gradual basis or not, it's not so simple. So let me just mention that there is at least a bound. So this is still something from chapter 3, bounds on Gradual basis. So if I have a matrix A, let delta A be the maximum absolute value of the determinant of a minor, the determinant of a square submatrix. That's a common notation because it affects complexity in various ways. You have a matrix, and delta A denotes the maximum absolute value of the determinant of some square submatrix. A matrix is totally unimodular if this delta A is 1. So it's an integer matrix, right? Data we are looking on an integer matrix. So A is TUM if and only if this is a 1. And so we can give the following bound. I'm not going to prove it, so here are some bounds. On any norm, you can actually get some bounds. So for every vector in the Gradual Basis, we have, let me give you 2 bounds. Bound on the, let's say let's start with the infinity. So the maximum entry, the maximum absolute value of any entry is bounded by n minus r times delta A, where r is the rank. Of course, it's less than or equal to mn. So you have this bound. If you don't know the rank, you just put an m there, or it doesn't matter. And G1 is less than or equal to n minus r plus 1 delta A. So this tells you that the Gradual Basis is contained in a finite box. In a set of all non-negative integer vectors which satisfy these bounds. So both bounds, for example. So x1 less than or equal to this, x infinity less than or equal to this. And they're incomparable. There are sometimes some vectors this cuts off and sometimes this cuts off. But you have at least a finite box, and this suggests a finite procedure for computing the Gradual Basis. So it's not going to be undecidable like some of the problems, the harder problems of polynomial that Matthias mentioned. There's a finite procedure, but you see, usually it's not polynomial because it depends, the box depends on delta A, and delta A is exponential in the natural binary encoding of the matrix, because the determinant may be exponential in the binary encoding. Yeah. Yes, thanks, yeah. Inequality, of course. Yeah. Okay, so at least we know something about the Gradual Basis. But we want to now discuss classes where we can actually compute it in polynomial time. And these classes are actually, they will look a little bit restricted in the beginning, but they are very natural. I'll give applications, not today, but tomorrow I'll give some applications. So they are very broad classes. And also there's a universality effect. So in fact, we will show later in the second hour tomorrow, I plan to do this, that we get a different parameterization for all integer programs. Every integer program is going to fall into one of these classes that I'm going to define now. So, okay, so after this introduction, let me start with chapter 4 then. Chapter 4. And this is called n-fold integer programming. And so the basic definition is the following. We define a bimatrix. We consider what I call a bimatrix. So a bimatrix simply means a matrix with a partition of the rows into 2 blocks. So it is a matrix, but we keep in mind the partition into 2 blocks. So it's, and I call it an RS by T bimatrix. So we have R rows here, and S rows here, and T columns for both blocks. Okay, so this is an R by S, RS by T matrix. Bimatrix in particular, we may have sometimes this may be empty. But then this will be a 0 S by T matrix. One of the blocks may be empty, that's possible, or 0, or whatever. And now we define for every n for every positive integer n, we define the so-called n-fold product of A to be the following matrix, not a bimatrix. So we start with a bimatrix, and then we get a matrix. And the matrix is the following. We denote it like this. So superscript with curly, with round parentheses, n. And this is defined to be, well, it's a big matrix. Up here we put the original bimatrix, so the two blocks, and then we copy the first block horizontally n times, and we copy the second block diagonally n times. And we fill the rest of the blocks with zeros, 0 blocks everywhere else. And okay, so what are the dimensions of this matrix? So this is a matrix now, not a bimatrix. So it should have two numbers here, the number of rows, the number of columns. What is the number of rows? Well, an easy arithmetic. What? R plus n times s. You see R is here, and each one of those is s. S, S, S. And the number of columns, n times t. All right, because there are n copies, and each one of those has t columns. So, and now the idea is going to be the following. So this is a big matrix. And we are going to look, so let me actually say, so the idea is this matrix is going to be small, and actually fixed. So if it's going to be fixed, we are going to get polynomial time algorithms. If it's not fixed, but let's say it goes small, let's say logarithmically with n or something, then you still get something which is sub-exponential. So there's actually lots of room to explore what can be done. I mean, this is really a new thing. 2 years really we developed this theory. So there are still lots of things to explore here. But think about this bimatrix as being fixed, and n is variable. So then this matrix has variable number of rows and columns. It's a large matrix. And an n-fold integer programming problem is something which looks like almost a general linear program, but instead of A, we are going to have an n-fold matrix. Okay, so an n-fold linear or non-linear IP is one of the form mean or max some objective function such that an x equals b, and the same thing x in z. Well, which z? What's the dimension of the vector of variables? N times t. A is an Rs by T by matrix. And then all these vectors should be of the right dimension. So the lower and upper bounds are in Z infinity. Again, they may have plus minus infinity entries, so no bounds. And T and D is in the vector of the space of rows, so it's R plus NS. And F is defined some function Z and T to R, let's say. This is an n-fold, an arbitrary nonlinear n-fold integer programming problem. And the claim is that we are going to be able to solve this problem. So what we are going to develop, so our goal show I can solve this such IP in polynomial time. Time which is polynomial in the binary size of the nature of data here, which is B, L, U, and that's it. Plus some information on F, and sometimes info on F sometimes. I mean, we may need this F hat sometimes, but sometimes not. And N, I should maybe put N, but N, you see again, because these vectors live in this dimension, then I count at least one entry for each one of those. But let me, to make sure, just add an N here in unary. But it's actually, it's encoded already here. So each entry needs at least one. Usually I don't write it, yes. What? Yeah, so A now is fixed. So A is fixed once and for all for such a program, and therefore it's not part of the input. And as I said, you may look for generalization where A has small size, let's say logarithmic in n, and then you would like to include it as part of your input. But now the setup is that A is a fixed matrix once and for all, and the algorithm depends on A. So for every A, there is an algorithm. So A is not part of the input anymore, but this is a big matrix, and this is variable dimension. So I should emphasize this, again, in contrast to the theory of fixed dimension that Matthias is developing. This is variable dimension, large dimension, n times t. N is variable, t is fixed. Variable dimension. And this is very nice because in the application, which we will discuss next time, it's very natural to have. So you have a problem with variable number of variables, and that's very useful. Okay, so let me give you one important piece here which is needed for this. So I'm not going to go really in very close detail, but here is one key important thing. So gradual basis. I mean, we are going to use, of course, what we developed in chapter 3, the gradual basis. So let's discuss gradual basis of n-fold product matrices. So what is the gradual basis of an n-fold product? So for this, we need something like this. So let's look on the kernel of this matrix. So here is A1. A1 is an n-fold matrix. And now when I want to study the gradual basis, I have to look on vectors in the kernel. So non-zero integer vectors, which give you 0 of this matrix. So let me write them by blocks, or bricks. I think we call them bricks. So now x, we want this to be 0. Let me emphasize the two different blocks here. So x, the vector of variables, is this vector, and each xk is a block, a brick of size t. You see this? This encodes these equations here, right? So you get this brick times this one. This has t columns, so this is of dimension t, and so on, and you want 0. So these are the candidates for being in the gradual basis. And well, let us call the type of x. So the type of x is going to be the number of non-zero bricks. So the type of a vector now, an integer vector, is the number of non-zero bricks. Okay, let me now, so now the idea is the following. Well, okay, let me give the formal definition here, but maybe I should be less formal here and just say, so let me be a little bit less. Another issue is if the gradual basis is empty, then something is going to be zero. It doesn't matter so much. So let me just say that look on, okay, let me give the formal definition. No, I'd rather keep it this. So let's look. So suppose now n grows. N grows. For various n's, we have different gradual bases, right? So for varying n, various n have gradual bases g of a of n, which live in ZNT. And the idea, we are going to look on all of those simultaneously somehow. So not on one n-fold product, but the gradual basis of all of those, and you have larger and larger matrices. So it's a class of things. And now when you do this, obviously the type of elements is going to increase, right? I mean, you have larger vectors with more bricks, and you may have many, many bricks. So what it turns out, and again, the formal definition is there, which take care also of the case of an empty gradual basis or this, but it turns out there is a definition which makes sense. Okay, let me give the formal definition. So the gradual complexity of a bimatrix A is the infimum of all non-negative integers such that the type of x is less than or equal to g for all x in G A n and all n. Okay, so you're looking at the smallest, basically smallest non-negative integers that bound the type for all of those guys. Now, I mean, I'm writing inf, right? So is this, can this be finite, infinite? That's the main question. Well, it turns out that it is finite. So there's some stabilization going on. So after a certain n, the type is not going to increase anymore. And this turns out to be finite. So here, let me write it as a lemma. Lemma g of a is finite. A finite non-negative integer, finite non-negative integer for every a. This lemma is some history. I should mention some name here. It started with work of actually statisticians that worked on tables, and we will talk about tables in detail on tomorrow afternoon. So Oki and Takemura, they looked on tables, which are very important in application and a very important model of this theory. And then this was generalized by Santos and Sturmfels from here, and later on by Hosten and Sullivan. Because history, the whole development is, again, 5 years or so, 6 years. So there's a finite non-negative integer. The proof, you can find the proof in my book. It's worked out carefully there, but I'm going to skip the proof and just going to use the consequences of this. So, and actually, maybe I should just give some bounds. So I'm not going to do the proof, but let me give you a bound, which is a little bit surprising. So here's a bound. So bound. Well, actually, before, let me just say a word on the proof here. So look on this, on the blocks up there. Yeah. So let's look on the blocks. Is there a pointer here somewhere in this room? Pointer, no pointer. Ah, actually, there's one. Where? Ah, yeah, good. A nice one, bamboo, a bamboo pointer. Very good. And here's a wire, I don't know why, rope. It's a fishing pole. Right, it's a fishing pole. Okay, so let's fish for some gradual basis. So, x1, so look here. So to satisfy these equations, look first on these equations. The bottom ones, not these, but these. So what is the first system of equations? It tells you A2 times x1 should be 0, right? So what can we say about x1, the first brick? Exactly, A2. It has to be in the kernel or in the lattice of A2. The lattice, it may be 0, it may be non-zero, but it has to be, it's an integer. So this one has to be in the lattice of A2, and the same for all the others. So every brick has to be in the lattice of A2, right? So maybe I should, so every brick must be in the lattice of A2 always. And so what is a natural candidate for being in the gradual basis there? What would you guess? The vector of bricks, where each brick is in the gradual basis of A2, right? That's the natural thing. So you might hope that, you just look on bricks, where every brick is in the gradual basis of A2. A2 is fixed now. Its gradual basis is fixed also. So you can once and for all compute it. But unfortunately, this is not true. So it may happen that you need in the gradual basis some elements or some bricks are in the lattice but not in the gradual basis. But then still you can write them as a conformal sum of gradual basis elements. We discussed this and use these somehow, use this. And if you work this out, and again, you can check my monograph there, chapter 4 in the beginning. It is explained in detail. This leads, but somehow the key is that you look on this A2 in the gradual basis of A2. So xk is generally is not in the, so I mean often it is there, but generally it is not. But this somehow leads to the following bound. So the gradual complexity is actually, it's equal actually. This. So this is kind of looks like a magic, but it basically follows from this fact. So what I write here is the following. You compute the gradual basis of A2. A2 is fixed, so this is actually fixed. Okay? Now you write this one as a matrix. So you write GA2 as a matrix. GA2 now is a matrix of T rows, and the columns, you have many columns. And now you can multiply this by the matrix A1, you get a new matrix. Again, this matrix is fixed once and for all. You compute its gradual basis and take the maximum norm, one norm of an element. That's the gradual complexity. And So basically, for fixed matrix, you can do this computation in constant time. It's fixed, it's determined. But the problem, you see, you have the computation of the graver of something. And this is very, very hard, even for small problems. We will discuss this later. Even for very small matrices, sometimes you don't even know the answer. I'll mention this. So this is a hard invariant to compute. And it actually leads to very interesting invariants for graphs. And I will mention this also in connection to multi-commodity flows. There's a very interesting graph invariant which is related to this. And we don't know the value even for the complete bipartite graph on 3 and 4 vertices. So 7 vertices graph, we don't know what the number is. So if somebody heard about the Shannon capacity, for example, it somehow reminds the complexity. So I'll mention this later. But for now on, we just have a finite number, and this is actually one way to compute it. Yeah, so A2, you see the Graver base of A2. The Graver basis of A2, again, the vectors are in the kernel of A2, so are in dimension T. And I write them as columns now, many, many columns. Okay, so again, I explain this carefully in the book. But I write them, each Graver basis element which has dimension T, I write as one column. I get a big matrix. The number of vectors in this matrix is the size of the Graver basis of A2. And then I can multiply by this matrix, which is R by T. I get a bigger matrix and I compute its Graver basis. Okay, so how do we use it to get polynomial time computation? So let me give you a lemma. So let's move over here. So let's describe a lemma. Maybe. Another board hiding somewhere, no? Yeah. So here is the lemma. So let A be a fixed by matrix, fixed by matrix. Matrix, and with Graver complexity GA, and K some number less than or equal to the Graver complexity. Yeah, actually, I don't need the Graver complexity, just and K positive integer. K positive integer. And then for all n, let's say greater or equal than K, we have the following thing. So I'm going to look on the set of vectors in the Graver basis of the n-fold product which have type less than or equal to K. And this is going to be exactly the set of what I call n-liftings, and I explain this. N-liftings of elements y in the Graver basis of the k-fold product of A. Let me just see, I made it, I got it right, I didn't skip anything here. Yeah, so n greater or equal to K, this is good. Yes, precisely what I wanted to say. And then n-lifting is something very simpler. So what is an n-lifting? K is less than or equal to n. So what do I mean? I mean the following thing. This is X, and it has some bricks, and this is Y. So Y has some, well, how many bricks has Y? K, right? It's in the Graver basis of the k-fold product, so it has k bricks. So let's call them y1, y2 up to yk. And now I'm going to use it and lift it to somebody in the Gradual Basis of, or some element in the kernel of the matrix AN. And the way is simply I choose some k spots there and put these up, and the rest are zeros. So it's going to be 0, 0 up to some, well, let's just write it like this. y1, 0, and so on, 0. And then at some point I put yk, 0. So, I mean, is this operation clear? It's very simple. So choose one of the n choose k bricks and lift it up in X. And this is a simple operation. I mean, is it clear what I'm doing? There are n choose k possibilities of choosing k spots among the n possible bricks. I take the y1 up to k, lift them up there, and fill the rest of the bricks with 0, and I get an element, an n-fold element. Yeah, so the order doesn't matter because, so I mean, that's a good question, but the point is that you see the Gradual Basis there's a symmetry. So if somebody is in the Gradual Basis, then any permutation is also in the Gradual Basis, and therefore I get it for free. So I don't need to worry about the permutations. So therefore, it's enough to actually just leave them as they are. But in principle, you're right. I should have, taken all the permutations, but this is already down there, so I don't have to worry about this. And so we do this, and the claim is that if I start with the Gradual Basis of the k-fold product and I take all the n liftings, I get something here. The proof is very simple. It's a line, but let me say this over here maybe. Oh, we have time. Let me skip this. It's not so interesting. So it's very simple. So why is this? So consider, suppose you take a vector here. Let's do one direction. It says if and only if, right? There's equality. Suppose you take a guy here. So that's more interesting. Why we get all of them? Suppose there is somebody in the Gradual Basis here, okay? And it has type less than or equal to k. Consider any vector x in the Gradual Basis of the n-fold product, which has type at most k. So I look on these k bricks, the non-zero ones, and I now look on a smaller vector, just take them down as they are, I get a k brick vector. And now the claim is this k brick vector must be in the Gradual Basis of the smaller one. Why? Because if not, then there exists somebody in the Gradual Basis here which is smaller in this partial order. Right? And so then we take this smaller guy and simply lift it up again, and we get somebody smaller than this guy. So that's a contradiction. And it goes the other way around too. So it's really directly from the definition. So, so you can see this. I mean, there's two lines. Again, let's check the notes. It's very simple. But we have some more interesting things to say. So I'd rather skip this. Okay, so here's the immediate conclusion now from this. So here's a theorem. For every fixed RS by T by matrix A, there's a polynomial time algorithm. There is an algorithm that in time polynomial in n, that's a unique input now, computes the Gradual Basis of the n-fold product, which again, let me remind you, is contained in Z and T. we fix a bimatrix for every n. This is the only input now. It's given in unary. I mean, that's the natural number, not in binary. That's too good to be true. We can compute the Gradual basis, this huge set, in polynomial time, polynomial in n. And do you see the proof now? The proof is now simple. We have this lemma, we have this lemma, two lemmas. So what do we do? Well, let GA be the finite fixed Gradual complexity of A. So for every matrix A, I mean, you know, this is a little abstract. I should have given an example. Okay, I'll give an example after this. So, I mean, it's hard to understand this. Also, it's very hard to compute this Gradual complexity. But just remember, for every fixed bimatrix, there's a non-negative integer g of A. Usually it's positive, which is very important, very hard to compute. It will control the computational complexity of our optimization algorithms. And it's fixed once and for all. If the matrix, the bimatrix is fixed, this g is a fixed positive integer, non-negative integer. So it's there, it's not part of the input. You do not even need to compute it to get the algorithm here. And so now we do the following thing. So now, let's look on g of A of n. What is it? Well, it's just what I call g and k, g and g. Right? That's the point. So to get the Gradual basis, it's enough to look on g and g. G and g of A. Let me write this like this. G and g of A. So it's enough to look on all Gradual basis elements of type less than or equal to the Gradual complexity, because there are no others. And then by this lemma, so this is by this lemma, and by this lemma, this is the set of all n liftings of elements of the Gradual basis of the g of A fold product of A. Yeah? I mean, just I plug for k, I plug g of A. So I take the matrix A, I form the g of A fold product of it, compute the Gradual basis, do the n liftings. Now, how many are there? And so you can, so let's just look on the number. So what's the size of this? So the size, let me write the size, and it's clear that you can actually compute them in polynomial time also, but let me just say about the size. So what's the number? The cardinality of this guy is something like what? N choose g of A, n choose g of A times the cardinality of this guy. It's getting a little bit, let me write this here maybe. Okay, let me write this here. No, okay, here. I mean, this is important, so it should be visible as our board. So this is something like n choose g of A times the cardinality of this guy. And this is order n to the g of A. And this is the end of the proof. So good. So you see, so you know this is bounded by n to the g of A times some constant. This is a constant. That's important. This is now a constant. It's a huge constant. But it's constant, and not only that, so this tells you about the cardinality of the Gradual basis. About the computation, so what do you need to compute here? So here you need some feeling for complexity, I mean, for algorithms. What do you need to compute for the algorithm? What? No, you don't need this. That's exactly a good point I want to emphasize. What else? Which basis? The grader of A of G of A. Again, this is something you don't need to compute. That's exactly what I wanted to hear. So basically, I mean, so really, you know, when you apply this, you need to compute this. You need to compute the G, you need to compute the grader basis of A of G, and then do the n-leaf things. But in principle, they are fixed, and the algorithm depends on this. So actually, you can pre-process it, and this is part of your Turing machine. You can actually have your Turing machine built into this huge basis once and for all, and then your input is only n. So actually, I don't care about it. Theoretically, I don't care. Of course, in practice, you really want to. You need to compute it. And we are going to see this is very hard. So let me actually mention, since this is hard, and maybe I should give an example. Let me give one example, maybe. Maybe this example is not so interesting. I don't know. Let's see. That's not so interesting. I mean, the process of n liftings, you understand. That's easy, right? You take the bricks and you lift them. That's easy. So let me maybe should give you one example of something. Yeah, okay, let me give you one example of some, at least the grader complexity. So, and then I want to say something about this computation. So here's an example. It's not an example of computation, just so suppose my bimatrix is this. This is the so-called incidence matrix of the complete bipartite graph K33. Then G of A so in the notes, you can check the notes. There's an example of a smaller matrix which has greater complexity 2, and then it describes the liftings for A4. Maybe I should do it. No, one should not. So, and this one is bigger, not so big, right? K33. So, what is the greater complexity here? Well, it turns out this is 9. 9, it has nothing to do with the fact that there are 9 columns. This is a complete coincidence. So don't be misled by quick conjectures. I mean, it's much more complicated than that. So I'll say more about this later. But for the time being, so this means, for example, if I want to work with n-fold products of this matrix, and this is very important. This corresponds. We'll talk about this on the afternoon lecture tomorrow. So this corresponds to 3 by 3 by n tables. Optimization. So optimization over such tables takes roughly order n to the 9 time. This is the key. It's not completely because we still have to incorporate. But so let me stop here. But now I want to actually conclude the theorem and say something about optimization. So here is the conclusion. Let me summarize this in a conclusion over here. Here is a corollary. So here is a corollary, or a big theorem here now. Theorem. And so polynomial times means, again, L, U, B, maybe F hat, let's say plus N maybe, to emphasize this, but we don't need this. Let me say N plus this binary encoding of the data, solving polynomial time, the following linear and non-linear IPs in variable dimension n times t. So actually, let me, instead of copying the set all the time, varying dimension t over the set over S, which is defined by this n-fold matrix. So set of all vectors satisfying this and this. So 1, minimize separable convex function. 2, optimize or minimize or maximize linear function, linear and 3, what else? Well, there are all these norms, let me continue here. Minimize norms. Minimize norms. Minimize norms. P between 1 and infinity. Find closest point to a given point. I mean minimize we can minimize find the closest point. That's important in various applications, error correcting code. Think about error correcting code. You have a message, you send, the receiver gets this X hat, which has some noise, and then you want to recover the feasible point, which let's say is a code word, which satisfies some parity check constraints or things like that to get the best one. So in tomography, this is finding the closest point is very applicable. Sometimes this is called projection onto the set. The set S projection of X hat. So finding the closest point in the set. 5, we can do an extended version of this, which I'll use later. Okay, maybe I'll skip this one now. And the maximization of FWX again, W is d by n, d fixed, and F is an arbitrary convex function on d-dimensional space, convex, not necessarily separable convex. And I should say something here, I should say something. So last time, actually, I told you that we can do this if we have the Gradual Basis. But it doesn't follow directly from what we've done so far. We need some more, for this one, we need some more geometric contents. And this builds also on results, geometric results of chapter 2. So I hope to say something on this very rough outline of the main theorem in chapter 2 on the last lecture on Friday. But in the lecture here, I decided to postpone it and concentrate first on this algebraic gradual basis approach. And these results apply also to combinatorial optimization. If you remember from my introductory talk, there's this branch of combinatorial optimization, problems on graphs and so on. So this applies to combinatorial optimization too. Okay, so let me conclude the lecture by saying something about the heuristic here. So you see the complexity here is not so, it's polynomial, but we get large exponents. And it's going to be even worse later. So let me just say something about the natural heuristic. And heuristic, I mean, so you've seen this last week quite, I mean, this was really the underlying theme in Jia Wang's talks. There's certain heuristic. There's a parameterization, there's a scheme, there's a parameter. The parameter was the degree of, say, these relaxations. You fix the parameter, then you can do things efficiently, and you hope for the best. Either you find a certificate there or not. And then you can increase the parameter. And so there's a trade-off between the complexity and and the precision in this sense. So here we have the same thing. So here is a sort of heuristic. Let me call it a scheme. So I have a whole section of this on this in the book. I'm not sure if it's in the preliminary version, maybe not. So section 4, gradual approximation scheme, I call it. A gradual approximation scheme. Scheme. And for this time, for n folds, and later we are going to generalize this to any integer program by the universality. Later, let me just hint chapter 5, to any IP. Universality. And the scheme is very simple now. You see, so let's just look. So fix parameter k. Let's say between 1 and g of a, the gradual complexity of your bimatrix. Compute in time roughly order n to the k the set, which I defined over there, gnk, is still on the board, isn't it? Maybe it got lost somewhere. Anyway, so let me write it again. The set of all x in the gradual basis of an of type less than or equal to k. And you see now this is, what can we say? I mean, this is contained in the true gradual basis. Right? And I need 3 more minutes maybe, and then we'll stop. You see, I mean, this is contained, right? Why? Because what is the true gradual basis of the n-fold product? The set of all elements in this gradual basis of type at most what? G of a. Right? So if I take k to be equals to G of a, then I get really equality here. And as I increase k, I get larger and larger sets. So I get that's why I call it a scheme. We have the following situation. We have G of n, let's say 1, not 0. Well, 0 is maybe the empty set, but so this is contained Gn2, and so on, all the way up to Gn G of A, and this actually equal the two Gradual bases. So we get approximations of the Gradual basis. It's a scheme. I choose the parameter. The complexity of computing one of those is n choose k. So let's start, for example, with k equals 2. There's a small complexity, low complexity, n squared. K equals 3, n cubed. And now what do we do with this approximation? Now use gnk to iteratively improve an initial feasible point of your n-fold IP using the algorithm from last lecture, using the algorithm from last lecture, which is the contents of chapter 3, as far as possible. So at this point, let me remind you what I just need 2 more minutes. You remember the algorithm from last time? I start with a feasible point. I have to actually find it, but suppose I have a feasible point. And then what did we do? Each time we went over all elements in the Gradual basis and looked for the best step size that we can improve the objective function, let's say minimize a separable convex or linear function. And if you find a better one, we went there and kept on doing the same thing until we got stuck. And if we really had the 2 Gradual bases, then we showed we get an optimal solution and in polynomial time. Here I'm suggesting take a subset of the Gradual bases and see, you keep going, improving until you get stuck. If you get stuck, you get some solution. It's a feasible solution always, and it has an objective function value. So you get a sequence of points now corresponding to these, you get a sequence of points. Let's call them star, I don't know. So these are the optimal ones you get from these programs. XGA star. And what can we say about XGA star? And that's the real 2 optimal solution, which let's denote by X star. And the objective function value, suppose we are minimizing, then they keep decreasing. And this is really the optimal objective function value. So this gives you a very nice scheme, very natural, and it has several advantages. First of all, if you go all the way to the Gradual complexity, you solve the problem to optimality in polynomial time, an integer nonlinear program. If you stop at some point below, you get something approximated, and then you have to decide, So I should say that X3, the third one, is really very interesting. Let me circle this. So if you do this one, you get complexity of n choose 3, n cubed. You get a very non-trivial augmentation procedure. And then you get some optimal value. Now you may want to compare it to some continuous relaxation and see how far you are. That's not so easy also, but suppose you know somehow that you are 20% from the optimal. And it took you 2 days to compute. No, I mean, these problems are very hard. So you say, fine, okay, let's stop. Or you increase k to 4, let it run, and you see that after 2 weeks you get nothing. And you say, okay, no, I have to stop now. That's the best offer I can do. If I make a contract, I compete for some contract, maybe my opponents do not know this theory. There's no way they're going to get a better offer. So you might as well stop. So, and let me say that the third approximation scheme already gives you a very non-trivial Gradual basis element appear there. There's no way you can understand from where they are coming, and this is something which is really important to explore. So people that are doing approximation algorithms, this is a different type of approximation, and there's lots of room to try and get some quantitative results on the quality of the approximation. It's very difficult, and I currently have a student that is working on this, trying to understand better what can you get with the third approximation. So that's yeah, so maybe I should, so anybody here knows about local search neighborhood approximations? You just switch locally, there's a neighborhood of the solution. So somehow there's a whole line of research there which is called K-optimal solution. You do switches. And somehow this K corresponds to switches. So 3 means the 3 opt. It's a certain neighborhood, but this gives you some nice vectors, and this is not ad hoc. This is a generic way of getting this. So I think this is very important practically also. Okay, so next lecture we are going to talk about some application of this theory, and so let's stop here.